Hello, welcome to the 7th lecture in ML series. In this lecture, we will be discussing what is version space. Version space is a set of all hypotheses which are consistent with the training examples and how compactly a version space can be represented. Let us quickly recall what we had discussed in the last lecture. In last lecture, we discussed our first machine learning algorithm called finds, which takes set of training examples as an input and returns one hypothesis, that is maximally specific hypothesis, which is consistent with all the positive examples and which may not be guaranteed to work well on new or unseen data, and as it ignores the negative examples, we cannot say whether it correctly classifies the negative examples or not. And even if the data is having a noise or inconsistencies, finds returns one hypothesis without actually checking. Even when you have multiple hypotheses, it is going to return only one hypothesis. So we need a method which should consider both positive and negative examples, and which should return set of all hypotheses which are consistent with the training data. That's where we had an algorithm called candidate elimination. But before going into the candidate elimination, we will be discussing a version space, how this set of all hypotheses which are consistent with the training examples can be represented. So now let us quickly understand why we will get a case of multiple hypotheses. So finds gives only one hypothesis, but if there are multiple hypotheses, they may generalize well compared to a single hypothesis. So let us consider a simple description of my friend likes bananas, my friend likes mangoes. From that description, if you have to get a general rule, one general rule might be like my friend likes yellow color fruits. It could be a general rule. Or my friend likes sweet fruit. This could be another. So both rules are matching with whatever the description that is given. If we can find both rules, then it is going to work well on real or unseen data. So that is our goal. We have to find set of all hypotheses which are consistent with the training data. Now, so how this set of all hypotheses which are consistent with the training data is represented? So that's where we have a version space. So version space is formally defined by using VSHD. H is the set of all hypotheses, D is the training examples. So from those set of all hypotheses, the subset of hypotheses which are consistent with the training examples. Consistent means correctly classifying all the training examples. So those we call it as version space. Now how can we represent this version space? So now version space can be represented by using general boundary and a specific boundary. So what is this specific boundary? So specific boundary is the set of maximally specific hypotheses that are consistent with the training examples. And general boundary is the set of maximally general hypotheses in H that are consistent with all the training examples. Let us try to understand this one with an example. So let us consider this example that we had discussed in the earlier lectures. So we had all the factors of 12 and a divides relation, and we had seen that this is a lattice, and then we get a Hasse diagram like this. Now suppose that we wanted to represent all factors of a 12 which are divisible by 2. Now it can be represented with a general boundary 12, because there is no number above 12, which is a factor of 12, and a specific boundary 2, there is no number which is less than 2, which is multiple of 2. So this 2, 4, 6, 12 is a set of points which satisfy that, but we can compactly represent it by writing simply 12 and a 2. Similarly, we have another example. All the factors of 12 which are less than 8. So now for this the general boundary is 6, 4. There is no number which is less than 8, which divides 12 other than this 4 and 6. And similarly, there is no number which is less than 1, which divides 12. So we can represent with a specific boundary 1. That means the set of points which satisfies 1, 2, 3, 6, 4, which can be compactly represented by using 6, 4 as a general boundary and a specific boundary 1. Now we will try to understand this one with our example. So let us consider this Enjoy Sport data set that we had seen in the last class. So they had given 4 examples, 4 training examples, and a find test returns this hypothesis: sunny, warm, question mark, strong, question mark, question mark. So this is a hypothesis which satisfies all the training examples. Not only this hypothesis, if you consider the sky condition is sunny, and the air temperature can be anything, and humidity can be anything, and wind is strong, and water condition is anything, and forecast is anything, is also consistent with these training examples. Because if you consider all positive examples where you have sunny in sky and wind is strong, so that is also consistent with the training examples. And in fact, sky is sunny and remaining can take any value is also consistent. Like that, there are 6 hypotheses which are consistent with all the training examples. Now the question is, there are 6, how compactly those 6 can be represented? As you can see that sunny followed by all question marks, is more general than sunny and a wind is strong, and remaining can take any attribute values. So now how compactly these can be represented? So these can be represented. So these are the 6 hypotheses which satisfy that those training examples. Now we can see that sunny, warm, question mark, strong, question mark, which is the most specific hypothesis that we got from the finders. And if you observe, sunny followed by remaining attributes can be any value, and the air temperature is warm and remaining attributes can take any value. So air temperature is warm, remaining air temperature is warm, then it is yes. That also satisfies. So followed by all question marks is also the general hypothesis. This forms as a general boundary. Okay, so now it can be represented by using simply S and G. Remaining all hypotheses which are between this S and G in the lattice also satisfies these training examples. Now the question is, how do we find this S and G by using a candidate elimination algorithm? So before seeing any training examples, we know that the specific boundary that is on top of a lattice, we have all question marks as it matches nothing, and similarly at the bottom of the lattice we have a general boundary which contains the most general, so now which matches everything. Now this version space contains set of all hypotheses. Now with every positive and negative examples, we have to update your S and G. So with the positive examples, we have to make a specific boundary more general. We have to update the specific boundary. And with the negative examples, we have to make the general boundary more specific. Because general boundary is expected to say true most of the cases, so we have to make more specific so that the negative example is satisfied. And at any time from G and S, the hypotheses which are not consistent with the training examples are removed. Okay, so this is what the candidate elimination algorithm does. It takes a positive example and a negative example and it updates G and S. Whatever the G and S at the end of the all training examples, that forms as the general and a specific boundary of the version space. Now, so in the next class we will be discussing how exactly a candidate elimination algorithm gives this G and S on this Enjoy Sport dataset. Thank you.